Welcome back, everybody. This is our third session in JEE Mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made two videos in this series, and both of those videos are available on our channel's playlist section. We have also started a similar series for NEET previous years, so if some of your friends are preparing for NEET, then you can guide them through those videos also. And if you find these videos useful, helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we completed with up to around 11 or 10. Yes, this was the last question. Now let's move to the next one. A very long solenoid of radius r is carrying current I, given by this equation. As a function of time, counterclockwise current is taken to be positive. A circular conducting coil of radius 2r is placed on the equatorial plane of the solenoid and concentric with the solenoid. The current induced in the outer coil is correctly depicted as a function of time. So we have to find out current, and then we have to plot a graph for that. Means we have to find graphical representation of the current. So first of all, let's draw a diagram. We have a solenoid of radius r. So suppose this is our solenoid of radius r, and then we have a coil of radius 2r. So suppose this is our coil of radius 2r, which is concentric with the center of the solenoid. And current is flowing in the solenoid, so solenoid will be producing magnetic field here. And due to that magnetic field, there will be a flux introduced within the coil, and due to that change in flux, there will be induced EMF in the coil or induced current in the coil. So we have to find out relationship for that current. So to find out the induced EMF inside the coil, induced EMF will be given by, let me make it slightly thinner. It will be given by negative of d phi by dt. This is the amount of the flux linked with the coil. Now, amount of flux linked with the coil will depend upon the area of the coil and also on the magnetic field produced by the this solenoid. So it will be minus d by dt b a into a area. Now area is constant for here for this coil, and let's write out the formula for magnetic field. Magnetic field will be given by due to solenoid, it will be mu node n is the number of turns per unit volume per unit length into the current and into area. So here all of these things, mu node n and area, all of these things are constant. We just need to find out the variation of I with respect to time. So this will be reduced to negative mu node n a di by dt, and we have an expression for I mentioned here. So I of t is given by kt e raised to power minus alpha t, and if we find its derivative, so it will be di by dt is equal to k times k will be constant here, e raised to power minus alpha t plus t into e minus alpha t, and derivative of minus alpha t, that will be minus alpha. So this will reduce to k e raised to power minus alpha t common 1 minus alpha t. So that will be the value of di by dt. So substituting this value here of di by dt, it will become mu node n a k e minus alpha t with my negative sign here, and 1 minus alpha t. So this is the value of induced EMF. And while analyzing this whole expression, mu node is constant, n is constant, a is constant, k is constant, e raised to power minus alpha t. Here t is variable, so this will be variable. So we can write it this whole value up to this as a some constant c. So EMF will be some constant c into e raised to power minus alpha t into 1 minus alpha t. Just to represent it in a simpler form, this we combined all of these constant into a single term. And now from is this expression of the EMF, when we can see that this EMF will reduce to zero, and it will reduce to zero when 1 minus alpha t is equal to 0, or we can say t is equal to we can t is equal to, it will become 1 by alpha. This is the one condition when this whole expression will reduce to 0, and also this expression will also reduce to 0 when this value, I can write it like this, c into 1 minus alpha t divided by e raised to power alpha t. I can write it like this, and from this we can gather another insight. As t reaches to infinite, as time reaches to infinite, this exponential term or this denominator term, as it is exponential term, it raises to very high value, and this whole EMF or value of this whole EMF again reduces approximately to 0. So first, initially, time is equal to 1 by alpha, it is 0, and when time is equal to infinite, or we can say very high value or very large value, it will reduce to 0. So let us find out that which of the following cases are shown in the graph. Now in graph, we are shown graphs are given current versus time. We have EMF versus time. So similarly, we can form current from this equation. So current will be E by R. So it will be C by R into e raised to power alpha t 1 minus alpha t. So again, current will be 0 when EMF is 0. So current will be 0 at t is equal to 1 by alpha, and current will be 0 at infinite when time is very large. So when time is very large, in all of these graphs, current is 0. So that's okay for us. So all of the graphs satisfy this condition. Now coming to this condition that t is equal to 1 by alpha. So in the middle of the graph, or in the somewhere in the middle of the graph, there will be uh, some point at which current is 0, and in these two graphs there is not a single point between the graph, in the middle of the graph or in the somewhere between in the graph, that at which point current is 0. But here in this graph A and graph that is B, I think, yes, in option A and in option B, we have we have a point here, and we in option B also we have a point here where current reduces to 0. So option C and option D are will not fill this criteria, and option A and option B will fill criteria. So one of them will be the right answer. Now let's further do our analysis. Now to differentiate and find that whether this induced current, this current is the induced current, it will be increasing or decreasing with time, we have to find out the behavior of our original current. We know that our induced EMF is induced in a such a way that it opposes the its causes. So we can let me write it that EMF is induced in such a way that it opposes its course. Means if our actual current or if current through the solenoid is increasing, if current through the solenoid is increasing, then induced current will be opposite of that. That means it will be decreasing, or it will have the negative sign. Actually, we can say if our current is increasing, is positive, then induced current will be negative. And if applied current or current in the, we can say, solenoid is in the negative half, then the current in the induced current in the solenoid will be in the positive half. So we will use this equation of the current to find out that whether this current is increasing or decreasing, or it is positive or negative with respect to time. So for that, what we have to do, we have to use we have to find out its first derivative, and then we will find the second derivative, and then we will analyze that uh, whether the current is increasing or decreasing. Now regarding first derivative, we have already solved this, so let me copy this. As up to first derivative we have already solved. Now we have to use the second derivative. So copy and paste it here. So this is our first derivative of the current through the solenoid. Now let's find out the second derivative. So second derivative, d square I by dt square will be equal to k as it is. Derivative of this, so it will be e raised to power minus alpha t into minus alpha with 1 minus alpha t. Now plus e raised to power minus alpha t as it is, into derivative of 1 is 0 and minus alpha t, it will be minus alpha. So we can take minus alpha e raised to power minus alpha t common, and we will be left with 1 minus alpha t, and here we will be left with plus 1. So we will have minus alpha e minus alpha t 2 minus alpha t. Now we will find its maximum minima, and to find maximum minima, what we do, we take first derivative and equate it to 0, and then find out a point in we can say inflection point at which there are changes happening. So this is the first derivative, and if we put it it is equal to 0, then times comes out to be 1 minus alpha t will be 0 and time will be 1 by alpha. And if we put this value of time here in the second derivative, we will get minus alpha e raised to power minus alpha into 1 by alpha 2 alpha 1 by alpha. So it will be minus alpha e raised to power minus 1, 2 minus 1 is 1, so minus alpha by e. So this is a negative value, and negative value represents that at this time our actual current is maximum. At this time our actual current is at its maximum peak. It means from 0 to t, if I plot a graph here, that this is our I applied, our actual current, and here we have time small t, and this time here we have 1 by alpha. So at this time current reaches its maximum value. So our applied current should start like this. At t is equal to 0, it is 0, and t is equal to 1 by alpha, it reaches its maximum value. So our actual current behave like this, and then it start decreasing. So suppose then goes like this. So if our actual current is behaving something like this, then our induced current, which is directly proportional to it but with opposite sign. So it will behave in a opposite manner. So in short, our induced current in the initial time should be negative, and when after reaching this point, when our actual current start decreasing or our di by dt becomes negative, our induced current should be positive. And after that, as our current is kept on decreasing, we assume it is kept on decreasing, so it should stay positive. So our induced current should look like this, that it should have some curve like this. At this point it should be 0, and then it should start going in the positive direction, something like it should be something like this. And our option A is the right fit for this. Now some of you might think from this graph that initially our applied current looks in a straight line. So, and our we can say induced EMF is directly proportional to di by dt. So induced EMF will be straight line, but it is just a way of representation. Actually, our induced current is followed by this expression, so I cannot actually draw that how it will behave. We just know from this derivative analysis that it will peak at this point, and before and initially putting t is equal to 0, at start it was 0 and it peaks at this value of t is equal to 1 by alpha. So we just uh, drawn a curve, and it looks like a straight, but it necessarily does not mean that it will be a straight line. It may take some curvy path. So the induced current will be, first point is negative in the initial, and will become positive. And regarding that, you can also get idea from here that as our induced EMF was negative, so initial current will also be negative. So hence all of these in combined, option A will be our answer. Now let's move to the next one. Two coils P and Q separated by some distance. When current 3 ampere flow through coil P, the magnetic flux 10 raised to power minus 3 Weber passes through Q. No current passes through Q. When no current passes through P, a current of 2 ampere passes through Q. The flux through P is. So we have to find out the flux through P, and this type of question can be solved with the help of the flux formula. As we know that flux linked to any coil is given by magnetic field passing through coil into its area. Now, flux linked, initially we have been given that magnetic flux that passes through Q. So magnetic flux linked with coil Q will be equal to magnetic field produced by coil B, because both of the coils are linked, and at a time only current in flowing through one of the coils. If flux is linked with coil Q, then it will be due to some other coil's magnetic field, and other coil is coil P. So flux at Q will be equal to magnetic field of coil P into area of coil Q. And similarly, flux in coil P will be equal to magnetic field due to coil Q into area of, we can say, coil P. Now they have some distance and their areas are not given to us. So what we assume? We assume that coils are identical. If these coils are identical, means their areas are equal, then we can write that phi of Q by phi of flux at P, their ratio will be equal to magnetic field at P due to P and magnetic field due to Q. Now both of these are coils, and in these type of questions, as we know that magnetic field, suppose we have a coil here, so magnetic field at the center of the coil, we know that it is given by mu node I by twice of the radius of the coil. Now if we take some random point here, then we don't have the value of magnetic field for that point. We don't have the formula. So if we taking any random point inside, we just approximate it equal to the magnetic field, equal to magnetic field at the center. So same we are going to do here, as both of the coils are coupled. So we assume this is our first coil and our second coil will be something like this. Our something coil is second coil is at some distance from it, or if I draw, this is our first coil and this is our second coil. And magnetic field at the center of one coil due to second coil is equal to magnetic field at its own center. So BP, we can write it like this: phi Q by phi P. Now BP is the magnetic field produced by the coil B, so it will be mu node IP divided by twice the radius of coil P divided by BQ, so it will be mu node IQ twice the radius of the second coil. And as we assume that both of these coils are identical, it means their radius are identical. So 2r get cancelled and mu node get cancelled. From this, phi at Q divided by phi at P is equal to IP divided by IQ. And now we have the value of flux at Q. This is the value of flux at Q. So this is 10 raised to the power minus 3 flux at P. Now I in P, that is 3 ampere, and I in Q that is 2 ampere. So phi P, flux in P will be 2 by 3 into 10 raised to the power minus 3, that will be 0.66 into 10 raised to the power minus 3, or 6.6 into 10 raised to the power minus 4. So that is option A for us. Now let's move to the next one. The self-induced EMF of coil is 25 volts when the current in it change in a uniform rate from 10 ampere to 25 ampere in 1 second. The change in the energy of the inductance is, so we have to find out change in energy of inductance. We know energy of inductor is given by half L I square. So we have the final and initial value of the current, just we need to figure out the value of inductance. And for a self-induced EMF, we know that self-induced EMF is given by L into di by dt. So value of E is 25, L we will calculate, di is 25 minus 10, that is 15, change in current by change in time, that is 1. So from this L comes out to be 25 by 15, that will be 5 by 3. Now initial energy will be half L. Initial current is 10 ampere, so 10 square, and final energy is half L, that is 25. Oh, sorry, L as it is. Final current is 25, so 25 square, or we can say change in energy, that will be final minus initial. So L by 2, 25 square minus 10 square. L is 5 by 3, so it will be 5 by 6 into, this is a square minus b square, so a minus b, a plus b, 25 minus 10, 15, 25 plus 10, that is 35, and this will be 1, 5, this will be 3, so 25 into 35 divided by 3, this will give us, this will be 2 here, because we divided it by 3. So this will give us 437.5 joule. That is option B. Let's move to the next one. A conducting circular loop made of thin wire has area mentioned, resistance mentioned, perpendicular time dependent field mentioned. The net charge flowing through the loop during t is equal to 0 to t is equal to 10 seconds. So we have to find the net charge, and net charge we can find out with the help of current. First we have to find current, and for current we have to find the induced EMF. Once we have the induced EMF, from that we can find current, and from that we can find the charge. So let's start. So expression for current is given by induced EMF by resistance, and induced EMF is minus d phi by dt. And here we have area fixed but variable field. So it will become minus 1 by r area outside into d by dt of magnetic field. Substituting all these values, minus area 3.5 10 raised to power minus 3, resistance 10. We have a derivative of the field, so it will become, this is B is 4 by 10 sine of 50 pi t. Its derivative will be 4 by 10 sine's derivative cos 50 pi t into derivative of 50 pi t, that will be 50 pi. So this 50 get cancelled here, 5 into 4 20 pi. So minus 3.5 into 20 pi into 10 raised to power minus 3 into 4 divided by 10 we have here, and cos of 50 pi t. This 10 cancels this. 3.5 into 2 is 7, into 4 is 28. So it will be minus 28 into pi 10 raised to power minus 3 cos of 50 pi t. Now this is the value of the current, and current we know that is equal to dq by dt. As we have to find out total charge between 0 to 10 milliseconds, so what we will do, we will integrate it here. So dq will become minus 28 pi into 10 raised to power minus 3. These values will stay out of integration. Integration of cos 50 pi t, and limits will be, initial limit, lower limit will be 0, and upper limit will be 10 millisecond, or 10 into 10 raised to power minus 3 second, that will be 10 raised to power minus 2. Now integration of cos will be sine theta, so it will be minus 28 pi into 10 raised to power minus 3. Integration will be sine 50 pi t with limits 10 raised to power minus 2 to 0, and it will be divided by 50 pi. Now further moving, pi get cancelled, and we have minus 28 by 50 into 10 raised to power minus 3. Putting the value of limits here, we will have sine of 50 pi into t's value is 10 raised to power minus 2, or 1 by 100, minus sine of 0, and that will be sine pi by 2, or we can say 1. So this whole term will be minus 28 by 50 into 10 raised to power minus 3. What we can do here, I can multiply it by 2 and divide it by 2. So this will become minus 56 by 100 into 10 raised to power minus 3 and further can be written as minus 56 into 10 raised to power minus 5. So it does not, our answer is not matching with anyone. Let me check. So I found the mistake. First, the mistake I made here, that 5 into 4 was 20, but I again also added 4 here. So this 4 should not be here. So it means that I have to divide whole expression by 4 here, and this expression again. So I have to remove 4 from here. We can say simply. So this will be 7, 7 pi. This will be again 7 pi, 7 pi here, 7 pi here, and 7 and 7 and 7 here. So let me correct for that. This is 7, this is 7 pi, 7 pi, and 7 pi, and here this will be 7. So this will be 14. So this will be 14. So it still it does not matches. It comes out to be minus 140, minus 1400 into 10 to the power minus 3, or 1400 millicoulomb. That is we are getting. And is there some mistake in the time? I think so. It does look like that there is a problem with the option here, that either some zero is missing or some typo error is here. So it should be 1400 millicoulomb, or we can say 140. Oh, sorry, not 1400 millicoulomb. It should be 0.14 millicoulomb. Either it should be this, or it should be 140 microcoulomb, or it should be this. But I think hopefully you got the process, that how we have reached to this answer, and you can try yourself, and if there is some error, then you can correct it yourself. So we end this video here with this question. Hopefully whatever we have covered till now is helpful to you. Again, if you find this videos useful, helpful, then do press the like button, and share it with your friends. And if you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. Also, if you like to donate us something, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.